It doesn't give me the equation, but it gives me at least the slope. So it's just everywhere I go, it's doing that limit for me. It's actually computing the limit. The computer is.
How do you do that?
I hit 1, which means one-dimensional analysis things, and then slider. And then I said, show me a tangent, and then just let me drag it around. So with this sort of idea in mind now, you start to go back and you start to think about some of the things in college algebra that we never even attempted to go after. Like when you were studying parabolas and you had the vertex, we had a formula, right? We had a formula for the vertex. So negative b over 2a, h was negative b over 2. So anytime anyone ever gave you a parabola, if the parabola opened down, we could always find the highest point. And if the parabola opened up, we could always find the lowest point, right? We could always do that. And that was cool to have that. But when we got past parabolas and we got to like cubic functions, or we got to like 4th degree or something like this, right? Let me, here's some crazy 4th degree function. We would be able to graph these in college algebra, but we would never go after these points, did we? In college algebra. We never went and tried to find the highest and lowest points, these peaks and valleys. We never did it. We just kind of waved our hands at it and said, well, we know it goes up and comes back and touches the x-axis at certain points, but we kind of had to concede to that, didn't we? But with this concept, would you not agree that to answer the question of where that point would be the same as answering the question as to where the tangent line slope is? Zero. Right? What's the slope of this tangent line right here? 0. So wouldn't all I have to do is take that weird limit and figure out where it's 0? Right? That's what I would have to do. If I could do that, then I'd be able to pick off these points. And that's exactly the way we do it. We're just not there yet. Okay, we still have a lot of work to do before that can happen. So let me do another example. Because the algebra of this one was pretty clean. Next one, not so much. So we want to find the equation of tangent line. To the function y equals 2x plus 1 over x plus 2 at the point 1, 1. So one thing I'll point out is that this is a little bit different than the last one, because in the last one I said at x equals 2, right? Here, and then we actually had to find f of 2 to figure out the y value. Here I actually give them both to you, don't I? If the problem is presented in this way, this x value is your a, and this 1 is f of a. Because they're giving you the base point, the x coordinate of the base point, and the y coordinate, or the y value of the base point. So this is actually more information than the last one being given. So don't you have a lot of the equation already? The key to it is going to be that slope, right? That limit. So can we go after that first? Let's go after that limit. The slope of the tangent line is equal to the limit as x approaches, in this case, 1 of f of x minus f of a. What's f of a? 1. They already told us 1. Over x minus 1. All I did was replace all my a's with 1s, right? And replaced f of a with 1 because it's also 1. And now I'll replace the f of x with f of x, right? 2x plus 1 over plus 2 minus 1 over x minus 1. All right. This is now your group quiz. You can work together. Everyone's going to turn in their own sheet of paper. I'm going to give you about, I don't know. No, 20 is way too long.
15.
Let's see if you can do it in about 7 minutes. Come on. It's just a limit. Just figure out what this limit is. Yeah, if you finish and you have time, go ahead and get the equation. But for now, all I want you to do is on a piece of paper, do this limit for me. And you can work together. Yeah, turn in what you have at this point. Right or wrong, I'm really going to be using this more of a participation grade. All right? A completion grade. I am going to do that, but what this gives you some indication of is, these limits are now going to pop up quite a bit, and so you need to be ready to handle them in a timely manner, all right? Because on a test, the most difficult part about the test is the balancing of the time and being able to answer all the questions being asked. If it takes you 35 minutes to do this one limit, there's no hope for you in a test. There's just no way you'll be able to get through the test. So this has to be, like I said, 10 minutes at the most to do a limit like this. The most, 10. All right, everyone's turned in?
You can save some time if you didn't have to write.
Turn in what you have, right or wrong. What's that?
So you can save some time if you didn't have to write a limit every time to do a direct substitution.
Yeah. Okay. I'm also going to pass around the attendance sign-in, and I have your quizzes from last time, so just thumb through this and grab your, I have all the old quizzes are in here, so you can just thumb through this if you don't have your quiz. Sign in, today is the 9th. So sign in and then grab your stuff out of here. Let's see if we can get this packet around in the next 20 minutes or so. All right, so what was the answer? See what the most common answer was. 1/3? Anyone else 1/3? A couple of 1/3s? Okay, so you have to get a common denominator here on the top. So when you put these two together, you get 2x plus 1 minus x minus 2 over x plus 2 all over x minus 1. So I'm getting the common here. I'm just going to assume you know how to put those two together. I'm doing that I did that in my college algebra class just the other day. So I'm assuming you can do that to here. That'll give you exactly what you want on top, won't it? It'll give you an x minus 1 on top. And that x minus 1 factor that's on top with your common denominator x plus 2 and then this other x minus 1 on the bottom, these x minus 1s cancel because it's like a fraction over a fraction. So it flips like this. And this is multiplication, and these two are gone. So you get 1 over x plus 2. Limit x approaches 1 of 1 over x plus 2, which is 1/3. So the slope of the tangent line is 1/3. And now, I didn't ask for this, but now we find the equation of the tangent line. So the equation of the tangent line, what we would do is we would do y minus y1 equals slope x minus x1, which was really for us y minus f of a, which was 1. Go back. Remember our point was 1, 1? Right? Wasn't it 1, 1? So the y value is 1. The slope we just found from there is 1/3. And then x minus 1 again. So we would get y minus 1 equals 1/3 x minus 1/3. Distribute. Add 1 to both sides. When you add 1 to negative 1/3, you get 2/3. So same thing here. Let me see if I can get this to do the same thing. My original function was, what was my original function? 2x plus 1 over x plus 2. 2x plus 1 over x plus 2. There's my original function. And what point were we at? 1, 1. And then the line that we came up with was 1/3 x plus 2/3. There it is. So that's the tangent line that hits that graph at exactly 1 point. We okay? Understand? Conceptually, do you understand what's happening? Okay. The actual computing of this is going to take a little time to get good at. Now, one of the results of this is something we can talk about immediately in terms of a real-world situation. If you recall, I kind of started the class with this notion that if you have some graph where on your x-axis is time, and this is like displacement, then if you have a graph, right, then displacement or distance if you want to. So imagine you have an object that's moving. They call this, it's called rectilinear motion. It's basically something moving in a straight line. Once you start moving things in 3D space, moving non-straight lines, things get a little more complicated. But if you got something moving in a straight line, car going down a road, whatever it is, then if you measure, let's say at some point in time A, you want to find the speed of the vehicle there, right? The speed, the velocity. Then what I could do before all of this is I could take another point over here, call that x, and then I could connect those two, and the rise over run here, right? The rise would be a distance, wouldn't it? So slope, this slope right here, the rise would be a distance, and the run would be a what? A time. And what is distance divided by time equal to? Velocity. That's your speed. So the slope of this secant line would actually represent your average speed over this time gap. So from time A to time x, that slope is your average speed. Understand? But with this idea, I can actually get rid of the whole other point, and I can take an object, time again, distance here. I can go to any point I want on the graph, and I can find that tangent line. And that slope should represent what we call the instantaneous velocity. So we used to have the issue that it didn't make sense to talk about the object, the speed of an object at an instant in time, because at an instant in time you go no distance and you go no time, right? There's no distance and no time if you're, like if I'm running and then I say freeze, and I say, okay, how far have I moved? How much time has gone by? I can't. I'm not moving. I'm not, But this idea allows us to get around that and actually talk about the speed of an object at an instant in time. So instantaneous velocity. Okay? And that's what these notes continue to go on to say. Where is it? Oh, wow. I went way too far. Sorry. I was like, what? Come on. There we go. All right, so now we have some notation. All right, some notation. And then we'll talk about the instantaneous velocity. This limit comes up so often. Okay, that limit comes up so often. And that's just, this limit is just the slope of the tangent line. That's all it is, right? It's not the entire equation of the tangent line, but it's just that slope part. That thing is so important to us that we have a special name for it, we have a special notation for it. And it's right here. This right here is called the derivative of the function the function f at a. This is the derivative of f at a. The notation we use for it is the f function with this little mark right here, and that's called a prime. And so the way we could read it is as follows. This right here is said to be the derivative of f at a, or f prime of a. F prime of a. So f prime of a, by definition, is this limit. Okay? If that's the case, then if you want to write the equation of a tangent line at x equals a, couldn't you rewrite the formula y minus f of a, but instead of writing that big ugly limit thing, just put right here what? F prime a, right? And then x minus a. So instead of writing all that big nasty thing, just write this and everyone understands that's what you mean. So the derivative of f at a is that. The derivative not only represents the slope of the tangent line, that's what I just told you, but also represents an instantaneous rate of change of the function at a number a. So I just said instantaneous velocity. All right, so that's one thing we have, instantaneous velocity. But it doesn't have to be instantaneous velocity. It can be instantaneous anything. So if this is time and this is distance, right, then f prime of a is the instant, I'm just going to put instant instead of instantaneous, instant velocity at a, right? That's what it would be? Because distance divided by time is velocity, yes? But what if you had a different scenario where you had, I don't know, maybe this was time, and instead of distance, let's say you were measuring something like, what's something you would do in like a chemistry lab? You mix something together, and okay, rate, yeah, that's a little more complicated than I want to get though. Temperature, right? Then you could have some graph. Maybe initially you start it, and the temperature is here, but then the reaction occurs, and then the temperature starts to come back down to room temperature, something like that. Then what would the derivative at a represent here? It's not velocity anymore, right? Like over here it was the speed at exactly that point. It would give you the speed. But here it's not velocity anymore, it's what? We don't really have a name. Like distance over time is velocity, but do we have something that represents temperature over time? No, so we would just say that this f prime of a here is the instantaneous rate of change in temperature. Right? That's all it is. It just gives you how fast the temperature is changing at an instant in time. So at this instant in time, the temperature was going up, right? The steeper this line is, the faster it's going up. The more shallow the line is, the slower it's going up. And then if it pitches the other way, then the temperature is starting to come down, right? But this measures the instantaneous rate of that change. And then change this time and temperature to anything you want, and the derivative will always represent what's happening as a rate of change at that instant in time, or that instant in whatever. Understand? So it's very global. The derivative does not have to be tied to time and distance or time and temperature. It could be anything you could imagine putting together on a graph. It could be time and profit for a company. It could be, I'm trying to think of things that are what we call continuous variables. Like I was going to say number of students and something, but number of students is going to be an integer. So you wouldn't have like 1.5 students, so it wouldn't make sense to have a graph. But we can relate any two variables together with a graph, and the derivative will apply. All right, so let's see if there's something in here that I can give you. 2.1. We have 10 minutes, so I think I have time to give you another one. Find capital F prime of 2 given capital F of x equals 5x over 1 plus x squared. So by the definition, f prime of 2, capital F prime of 2, this function is called capital F instead of little f, all right? It could be g, it could be h, doesn't matter, it's just a generic function. I want the derivative of it. By the definition, this is, let's see, should I call on somebody today? You have these name tags out. No, I won't call on you. I'm going to call on someone that doesn't volunteer. Is that okay? All right. Tony? How's it going? Do you know the definition of this? So capital F prime of 2 would be what? Or anyone at Tony's table. What's the definition of the derivative? Okay, limit x approaches a, but a for us is 2 of so that's your f of x minus what's f of a? F of a? What is f? But a is 2, so what's f of 2? See, you need to put f of 2 in here, right? So you actually have to go figure out what f of 2 is.
So you got to plug it in.
You got to plug in 2. It's not going to be 2, the number 2, it'll be f of 2. So 2 in here is what? 10 over 5, so it's 2? It's 2. It happens to be 2. But it wasn't 2 because we plugged 2 in, right? So f of 2 turns out to be 2. We got lucky. All over x minus 2. And then, at this point, common denominator, play your game. Yes?
Why x minus 2?
The definition, all right, capital F prime of A. Yes? Okay. Yes.
The only time you won't need to plug it in is when you actually are given 2 of the coordinates.
If you're given the coordinates, you don't have to do it.
Alright, cool.
So usually on tests, I don't give you the coordinates. I just give you the x so that you have to go get the a. Well, now you know. Now you know. OK. All right, so common denominator here, limit, x approaches 2. Let's see, we'll have 5x minus 2 times 1 plus x squared over 1 plus x squared over x minus 2. So I put these two together with like that, and I'm hoping for some good cancellation. In fact, I'm really hoping to get an x minus 2 up there that I can cancel out. Do I get it? What does that numerator become over here?
It'd be 5x
5x minus 2
minus 2x squared.
minus 2x squared.
You can flip it around, right?
Yeah, we'll rearrange it on the next line. We should be getting 0 over 0 here. Like if you were to plug in 2, we should get 0 over 0. You can probably tell right here. Plug in 2 here, we already know that that's 2. 2 minus 2 is 0, and then 2 minus 2 is 0. So we know we're getting 0 over 0. So I'm going to have to get this x minus 2 to cancel. How about we factor out that numerator? And here's the way I'm going to do it. Negative 2x squared minus 5x plus 2 over 1 plus x squared over x minus 2. So I pulled a negative out of the top because I prefer to factor something like that. Right, so I just changed the signs of everything, just put that negative out front. Can you factor 2x squared minus 5x plus 2? Yeah? It should factor to be, let's see, negative out here, and then what two things? What is it? 2x, x, 2 minus 1, something like that? So yes, you still have to be able to factor those types of things. Should I double check it? 2x squared minus 4x minus x, that's minus 5x plus 2. That works. 1 plus x squared over x minus 2. And what's great about that is that x minus 2 will cancel. So now plug in 2, and you should be good. You should no longer have 0 over 0. So 2 here, 4. 4 take away 1, that's 3. Negative 3 over
4.
5. Negative 3/5. That's the answer. See, I'm not asking for equation of tangent line or anything like that. It's just what's the derivative at A? At 2, it's this number. That's your derivative. Who has the folder? Has it gotten around to everyone? I just want to take a look at your homework assignment real quick and see if it's everything, if everything can be handled. Thank you. So we are working, tonight's homework is at a 2.1 in the book. Okay, so on the homework, I'm just going to say skip 38 and 47. This is for homework 2.1. So you should work on that. Remember that if for some reason, well, most likely the class on Monday won't be held, then you are also responsible for watching the video on 1.6 or 1.5, which is continuity. And taking a look at those videos and doing the homework out of that, and then come in on that following class period, and then we'll be getting pretty close to the test, won't we? Well, actually, if we do it that way, the next time we meet will be the day before the test, which means we would review. We would do a review that day. And our test will not cover everything that's on here because we have not done 2.2, 2.3, or 2.4. So we're going to be playing some catch up in here. That'll be on the next test, yeah. Unless we decide we want to push the test back.